Causal set theory is one of the most elegant approaches to quantum gravity. Its core idea is surprisingly simple. At the most fundamental level, spacetime is not a continuous manifold but a discrete network of causal relations. Proposed by Raphael Sorkin in 1987, it has developed over nearly 40 years. Today we discuss, how does causal set theory describe quantum spacetime? What successes has it achieved? What challenges does it face? Why do we need causal sets? General relativity assumes spacetime is a continuous manifold, but this assumption may fail at the Planck scale. Simply gridding spacetime breaks Lorentz invariance. Different reference frames see different grids. The core insight of causal sets is, causal relations are more fundamental than distances. In quantum gravity, first determine which events precede which, then determine distances. Lorentz invariance then emerges naturally from the causal structure without assumptions. The core mathematical concept is the partially ordered set, poset. A poset consists of elements and a partial order relation, satisfying transitivity and irreflexivity. Transitivity: if x precedes y and y precedes z, then x precedes z. Irreflexivity: no event precedes itself. In causal sets, each element represents a Planck scale spacetime event, and the partial order represents causal relations. Posets are naturally discrete, requiring no introduction of discreteness. The key construction is sprinkling. Randomly sprinkle points, Poisson distribution, in continuous spacetime, keep causal relations, delete distance information. The randomness of sprinkling guarantees Lorentz invariance. The Poisson sprinkling process is statistically equivalent in all inertial frames. The spacetime volume of a region is proportional to the number of elements in that region, with proportionality constant being the fundamental density ρ. The causal structure contains all geometric information of spacetime. The metric can be recovered from causal relations. Causal sets have achieved several major successes. First, Lorentz invariance emerges naturally from discrete causal structure without assumptions. Second, causal sets predict the cosmological constant lambda equals 1 over square root of n, where n is the number of elements in the observable universe, about 10 to the 120, so lambda about 10 to the minus 120, remarkably consistent with observations. Third, the spacetime volume formula V equals n times Lp to the fourth power gives volume quantization. Fourth, causal dynamical triangulations complements causal set ideas, with numerical simulations supporting the importance of causal structure. The first challenge is recovering the continuous spacetime manifold from discrete causal sets. The sprinkling theorem tells us that at large enough scales, containing many elements, the statistical properties of causal sets match continuous spacetime. But at small scales, the structure is very different. Local properties, dimension, curvature, are easy to recover, but global topology, shape of the universe, may differ. The Hopf-Vermeutung conjecture claims causal structure uniquely determines topology, but this remains unproven. The second challenge is dynamics. Causal set dynamics is growth-based. As time progresses, new elements are continuously added, and the causal set grows. Sorkin and Dowker proposed a discrete action principle based on element count. The growth process is stochastic, and dynamics is statistical. The discrete Friedmann equation dn/dt equals h times n describes cosmic growth. But the complete causal set dynamics theory remains unestablished, the biggest technical challenge. The third challenge is matter and dimension. How to determine the spacetime dimension from causal sets? The Mir-Heimmeyer dimension estimates dimension by counting elements in cones. In d-dimensional spacetime, the number of elements in a cone is proportional to or to the d. Matter fields require external introduction with no natural mechanism. The semi-classical limit is also problematic. How to recover Einstein's equations from the discrete structure of causal sets? These are the core technical challenges. Causal sets, string theory, and LQG are three different approaches to quantum gravity. Causal set's basic object is opposite. String theory uses strings, LQG uses spin networks. Causal sets are naturally discrete, string theory is continuous, LQG is quantized. Lorentz invariance emerges naturally in causal sets, string theory needs fixed backgrounds, LQG partially satisfies it. Causal sets successfully predict the cosmological constant, string theory faces the landscape problem, LQG hasn't resolved it. All three satisfy background independence. Causal sets are the most elegant with the simplest mathematical structure. Causal set theory is the most elegant approach to quantum gravity. Its greatest advantage is Lorentz invariance emerging naturally from discrete causal structure, and its greatest success is the cosmological constant prediction matching observations. The biggest challenges are recovering the continuum limit and establishing complete dynamics. Future directions include combining with machine learning to explore statistical properties, numerical simulations verifying the importance of causal structure, and finding experimental test pathways. Though less famous than string theory and LQG, causal sets' elegance and predictive power make them one of the most promising approaches. Thank you all.